All right, so we talked about a whole bunch of different learners. We've been taking the learning as function approximation point of view. Right, we're just basically learning is regression. You show me a bunch of chairs or a bunch of zeros and sevens or whatever, and you say that's a 0, that's a 7, and then after a while I learn what a 0 looks like and what a 7 looks like, and that lets me, when you show me a new picture, I can tell you what it is. So k-nearest neighbors, neural nets, I'm not convinced that's in focus. I demand higher performance. There we are. We looked at neural nets. We looked at basic old linear regression, which I'm in love with, if you haven't noticed, and then 3-layer artificial neural networks, which are much more expressive and impossible to train or decipher what they're doing. ILP, and then at the end of the last class, we looked at decision trees. I was expecting some questions about decision trees, but I guess people understand them. So that's what we've talked about so far. We have one more major kind of learner that we're going to talk about in this class, which is naive Bayes. There is a whole area that we're ignoring, if you want to get super fancy, called support vector machines, which we don't talk about. But they let you do things like implicitly learn with an exponentially large number of features in polynomial time, which is rather magical, through some very cute little thing called the kernel trick. Which we're not going to talk about. So let's talk about naive Bayes. Now, is everyone feeling all right? Because it's about to get worse. Sorry about that. The assignment is pretty straightforward, but the stuff we're going to talk about in class is about to get more complicated. This is the toughest part of the class, this last 2.5 weeks. We do this thing called Bayes nets. And we're just about to get started on that, maybe at the end of today or the beginning of next time. So just so you're warned, it's about to get. There's going to be a little bit more math. But luckily, you only have to remember one thing. That's the great thing about this part of the class is you only have to remember one thing, which is Bayes' theorem, and I can never remember it. So I'll tell you how to derive it, because it's impossible to remember. I mean, anyone who can remember that totally deserves an A. But I'll tell you how I derive it.
Listen, let's talk more about the A.
Whoops.
I think I might have it.
Let's see. Okay, here we are. So this is a new kind of classifier we're gonna learn about. It's based on Bayes' rule, and Bayes' rule is so popular that there are people walking around with T-shirts saying things like, I'm a Bayesian, meaning like, I am totally hip to Bayes' law. So I can never remember Bayes' law, so let's see if we can derive it. So things are about to get more complicated. This is what's called a joint probability distribution, and these are the kinds of things you probably didn't see in your stats class that you have to deal with in this class. It's a distribution over two variables at the same time.
It's a joint probability what?
Distribution. And let's just interpret this for the moment as the probability of A and B both being true. Let's see, so we have the probability of A and B. That's going to be the probability that A is true given that B is true times the probability that B is true. Everyone remember conditional probability? I think we had a picture a while back where we had something like, this big rectangle is the whole world, the whole probability universe, and maybe this is when A is true and this is when not A is true. And then, sorry, and maybe this is the place where over here B is true, and over here not B is true. So A given, if the probability that A and B are both true is the probability that A is true given that B is true times the probability that B is true. Well, B is 0.5%. Looks like A is true given B. Well, yeah, I don't know. But anyway, that's how one. If you happen to know these two things, you could compute that. The probability that A is true given that B is false is quite small, even though the probability of A being true, if we don't know anything about B, is quite large. Like, it looks to me like A is true with a priori with about probability 0.3. But if we knew that B was false, B were false, the probability of A being true would drop way below 1/4. I don't really know what it would be, but pretty darn low. Like, I'd say 0.2 maybe. So knowing something about B tells us a lot about A in this kind of world. Anyway, so it's not too hard to remember conditional probability. I mean, that's what you really have to remember. And if you know that, you can derive Bayes' law, because it's equally valid to say that this is equal to the probability of B given A times the probability of A. So that tells us that, and so now these two things are equal. So then we can do something like say the probability of B given A is just the probability of A given B times the probability of B divided by the probability of A. And that's Bayes' law. So it's not hard to get it when you need it. If you're bad with memorizing things the way I am, you just derive it straight from conditional probability. Okay, so now let's talk about what on earth, why would you ever want to be able to express the conditional probability of B given A in terms of these other things? Well, turns out that that's actually a super useful thing to know. So, for example, let's say that you finally went over to health services and got your annual checkup. And they give you a battery of diagnostic tests, and they say, let's hypothesize that you have, I don't know, some horrible disease. Yeah, I don't know. Pick your favorite horrible disease. Now, the prior probability of you having, that's H, horrible. The probability of you having horrible disease is quite low. Like, it occurs once every 10,000 people. Luckily, we have this great test, this great diagnostic aid that gives us some data. The probability that we would get a positive test result, positive data, if you actually have the disease, 0.99. Really nice. So if you've got the disease, there's a 0.99 probability the test will come back positive. If we just give the test to random people, the nice thing is that it only comes back positive 1% of the time. Right? So it's got high, I think this is called specificity, and low, I don't know, anyway, you don't get a lot of false positives. And so then you go to health services and they say, oh, dude, you got a positive test result. And now you're like, oh, crap, what's the chance I have the horrible disease? Right? It's looking pretty probable, right? Because this test is pretty freaking awesome. So you'd really actually be able to you'd really like to be able to compute this. Anyone want to give me a ballpark figure real quick off the top of their head? What's the probability you've got the horrible disease if your test comes back positive? Just roughly. Is it going to be like 99%? Is it going to be 0.9? You know, is it a 90% chance? Is it a 1% chance? Is it a 10%? Just roughly. 99. So we have widely divergent views. 50. So basically, you get the test result and you're like, what does this mean? I don't even know. You know, the scary part is they give this same test to doctors, and they don't know either. It turns out that humans are inherently like not built to understand what's called the prior. Just yeah. So if you do it the math, it's not too tough. So it's this times this. So this is all of a sudden going to get really small. As you multiply it by that, but then you divide by this. So this makes it small and this makes it big again. I guess if we divide these by each other, what do we get? 0.01, I think, right? Because this is 4 decimal places over and this is 2. So we divide this by this. So we move the decimal point over 2 places here. 1, 2. So it's about 1% chance that you have the disease, which surprises most people. Most people think, you go to the doctor, the test comes back positive. The test is, doesn't have a lot of false positives and goes off when you have the disease. Therefore, it came back positive. I must have the disease. But in fact, because the disease is so infrequent, you get a zillion false positives just because you're testing all the time. We used to have something up on the web page about this. Let's see if I can find. Bayes' rule. Here we go.
Don't trust doctors. Don't trust anything. Is the false positive based on a? I guess this isn't really pertinent, but is it based on a actual feature of the person, or is it random?
For like a test, is the false positive going to come back consistently false positive, or is it randomly false positive? So does testing more help?
Yeah, this scenario hasn't addressed that question yet. So, yeah, that depends on the nature of the test. Yeah. In the real world, my understanding is that there are tests that have lower false positive rates that are much more expensive to run, so that if you come back positive, then they give you the second test that's different. So it is independent. So doing this other test actually adds information because it's going to be wrong in different ways. And it's less wrong, and it's way more expensive. So instead of the 25-cent test, they're running the $15 test, which they charge you, of course, $300 for. Okay, so I think the reason I'm bothering to do this is it has these nice numbers in it. So in a population of 1 million people, 0.01% are infected, right? So that means 100 people. And 999,900 are not infected, right? And if the test is 99% accurate, right? 99 of these test positive accurately, and 9,999 of these test positive falsely. Right? So out of all the positives, just 1% are actually infected. Right? So it's the fact that this number is so big that is messing up all the statistics. All right. Does everyone understand this? So this is the magic of Bayes' rule. That even if you're 99% accurate, if you're testing 1 million people, you're going to get 1% of 1 million is 10,000. It's a lot. And if the disease itself is very infrequent, then these guys are going to be a small percentage of these guys. So, I keep opening the wrong window. That's Bayes' law. So the answer here is 1%. So now, this is Bayes' law. It's you're reasoning about a hypothesis given some data. Typically, people are pretty good at assessing these top two probabilities, at least. Like, what's the probability that in your assignment, for example, you're going to be wondering what's the probability it's a 7 given that I have this image. So H is it's a 7, and D is the data, these pixel values. Now you know you're going to have a pretty good sense of the probability that's a 7 because I'm going to tell you right now that we have this big pool of test data and it's equally distributed between all the digits, and we're going to pull out randomly. So the probability of it being a 7 is 0.1, 1/10. Now what's the probability we would get this data if it were a 7? That's not too hard to assess. You can look at a whole bunch of 7s and see how likely, you build a model of 7-ness. This is called a generative model because it's like, ooh, draw a 7. Okay. It's a forward model of generating 7s. What's the probability you'd see this if it were really a 7? How much does it look like a 7? That's pretty easy for people to get. So these are easier for people to get. This is harder for people to write down. Now, one problem is this denominator term here. Sometimes you don't have that. Anyone have a sense of what we can do about that? We apply mathematics and try and get the probability of D by some other way. One handy thing that often comes up, you can kind of create, if you happen to have a lot of conditionals about D, like if you have D given H, then you can start to get a handle on D if you know something about H, and we do know something about H. So the probability of D is just this weighted sum. We'll take the probability of D given H, and we'll take the probability of D given not H. And we have to weight those appropriately by the probability of H and the probability of not H. So you might say, well, wait, we don't know what this is, but you've been given this, and they have to sum to 1. All right, so the probability of not H is 0.9999. The probability of D given not H, I think we don't have. I think we're kind of hosed on that. But I gave you probability of D. So sometimes life might give you this and not this, in which case you can then derive the probability of D. Lee.
pH.
Probability of the hypothesis, yep.
All right, so in the 7. So we have pH D right there.
pH given D?
pH given here up at the top, very, very top. All of yes. That is the probability that it is a 7 given the data.
Yeah.
All right, and pH up there.
Probability it's a 7. The prior probability, knowing nothing, before I see the data.
What are the chances that I get a 7?
Exactly.
All right, and then pDH. What is the probability based
Of seeing this data, given that it is a 7,
what
divided by the probability of the data. So think of somebody coming in saying, oh my God, the Russians have launched their nuclear weapons at us. Right? So why do you think that? Well, the satellite thing is going berserk. So, okay. What's the probability that they're going to launch their nukes? What's the probability that if they did launch their nukes, you'd see the satellites going berserk? And what's the probability that satellites just go berserk on their own on any particular day?
It's divided by how wrong the test is, right?
Yeah, kind of. What's the, if this is something you see every day, like, oh, the sun came up. Like, dude, that's not sufficient evidence. Like, the sun is always going to come up.
It's divided by how unreliable it is, maybe?
Divided by false positives, right?
I guess you've told us how to compute PD.
The probability of the sun coming up, if they've launched their nukes, I guess, is 1. The probability of the sun coming up is 1. So really, if now our data is completely unreliable, right? Like this is always 1 and this is always 1, so these go away. So now we just are left with the prior. So in the case where your data doesn't tell you anything about the phenomenon, that just goes away and you're left with your prior, which is just the way it should be. If this is extremely rare, then that inflates this probability, which is what you want. Because, oh my God, it happened.
It's almost never wrong. Dividing by an incredibly small number is going to be very large.
Yeah. Well, notice this isn't conditioned, right? So there's no given h here. This is just the probability you'd get that data under any circumstance for h or not h.
Okay, so this is the reliability just of that data.
Yeah.
Just in general.
Dan?
Can you say in English PDH again?
The probability of the data given that the hypothesis is true.
That does not make sense to me for whatever reason.
Okay. Let's see. There must be a Sherlock Holmes thing here about the butler did it. The probability the dog barked. So if what's the probability that he did it given the dog barked? Well, what's the probability he did it? What's the probability the dog barked if he did it? And what's the probability, the background probability that the dog just barks? So if the dog rarely barks, that makes this positive, especially if the probability, if he did it, then the dog would bark. If that's a very high probability, then you're going to get a large number here.
Okay, I think I get it.
Yeah, conditional probability.
So in terms of our assignment.
Oh, we haven't gotten to that yet. That's the next slide. That's or here, the naive Bayes classifier. We'll get there. We're just doing the basics. Before we get to the naive Bayes classifier, just what the hell is Bayes? So that's what this is, Bayes. Bayes' theorem. He was like an English reverend, and he was into math, and he died, and his friend was going through his papers in his attic and found this paper and said, oh, this is cool, and sent it off to the Royal Society of London, who published it, and he became famous. Posthumously. Yeah.